Hello and welcome. This is the Public Affairs Forum, sponsored by the First Unitarian Universalist Church of Austin, Texas. My name is Luther Elmore. These forums are held on the second and third Sundays of most months. Come visit us at our church site, 4700 Grover Avenue in Northwest Austin. This church has been holding these forums since 1954, the year this church was first incorporated. We invite you to join us at noon or shortly thereafter on those Sundays. Today our speaker is Dr. Bruce Naylor. Dr. Naylor is one of the members of this congregation, and he'll be speaking about artificial intelligence or artificial everything, 2020 and beyond. Dr. Naylor holds a PhD in computer science. He's been an adjunct professor of neuroscience. He is currently an adjunct professor of neuroscience at Baylor College of Medicine. He will tell us about the current state of affairs as regarding artificial intelligence and possibly tell us where it might head us in the future. Would you please welcome Dr. Naylor? Bruce.
Okay, sort of the nominal topic, as he said, is artificial intelligence, but when I got into it, I realized there was a much bigger story of which AI is a part. And so I really wanted to give you this bigger story, and it has really a lot to do about the relationship of computing to the world in general. AI is a special case of that, a very important special case of it, where we're trying to mimic humans to varying degrees, various attributes of humans. But the machinery that's used for that, while it's become specialized in various ways, is part of a trend that's been an explosion really in computing that started in the 20th century and has continued unabated since the early days in the 1950s. And I think there are some, besides kind of like all the bits and pieces, I want to try and add more glue to the presentation than if someone got up and said, I'm going to talk to you on AI. So it's going to be a bigger context, and it will, I hope, to introduce you to more things that are going on in computing and how maybe get a sense of how they might kind of fit together and what some of the actually philosophical implications are. I think there's huge philosophical implications for computing success at simulating lots of things, AI being an example of that people are aware of because it intrigues us, because we're trying to, or gives us the impression that we're replicating ourselves with technology. And that's true to a certain degree. Okay, so I should confess that my core expertise is computer graphics. That's what I started out in. Got into AI in various ways. So video games, I spent a lot of time on technology for video games, and video games use a lot of artificial intelligence to have characters that you're playing against. And then I also started working 10 or 15 years ago in neuroscience, and so I used machine learning, which is part of AI, to analyze our brain readings using the readings came from MRIs, functional MRIs in particular. So I've been working with AI off and on to varying degrees for a long time, but the broader picture I'm going to position AI into actually has more of its roots in computer graphics, because computer graphics is really trying to simulate the entire world. It's not restricted to trying to mimic human beings. It's a broader agenda. Okay, so here we have some pictures basically ripped off from 2001: A Space Odyssey. And the point to be made, the title of the slide, The Human Tool Maker, is that humans have been making tools for a long time. And for a while, we thought that we were the only species that made tools, and that's what made us different than everybody else. But sort of every one of our pathways to feeling special always gets doused by facts that eventually come out, and we discover we're not so special. So there's lots of other species and all sorts of different parts of the animal kingdom that make tools. It's just we made the tools that we can write with and communicate and talk to each other. But my point is that it's a part of our nature, it's a part of other animals' nature, but in particular our nature, and what happened in the 20th century, second half of the 20th century, is a continuation of that. Okay, let me begin with the mathematical basis for reasoning. This is where computers come out. It turned out it's actually pretty simple, and it was because you had people in philosophy who had the topic of logic as core to their discipline for over 2,000 years. And interestingly enough, the logic course that's taught at UT is still taught by faculty in the philosophy department, even though the computer scientists, everything on computer science is built on top of logic. So Plato and Aristotle were talking about logic, and kind of nothing really happened dramatically until the 1850s when George Boole abstracted out and made a mathematical version of logic that was allowed a level of unambiguous rigor. So formal systems or mathematical systems, the main thing they do compared to normal human conversation is they eliminate ambiguity. 2 + 2 = 4. That's very precise. And that lack of ambiguity was critical for being able to do anything with computers. So George Boole started that. So it replaced common sentences with abstract symbols and called symbolic logic. And you had operations like and, or, not. They had formal versions of those rather than just casual conversation. That's the point of having a formal symbolic system, is as I just said, there's no ambiguity. But you could then have statements like P and Q imply R. If both P and Q are true, then R is also true. So no human being talks like that, except for in the mid-20th century, they were academics who made their career doing symbolic logic, and they'd actually get up and give talks where they were just rattling off symbolic logic statements. But in general, no one does that. But this was critical, not for humans, but to get to, as I said, to get to computers. And one of the steps in that process was a massive 2,000-page tome called Principia Mathematica, which was written by Alfred Whitehead and Bertrand Russell, both mathematicians, philosophers of the first order. And if you've, in this church, ever heard process theology, the term process theology, or had any exposure to that, process theology was based on Whitehead's focus on processes. And computing is the abstraction of processes. It's about process. And so it's not all that surprising that Whitehead made a contribution to that way of viewing things. Bertrand Russell made many contributions, but one of which, if you've ever had any work with computer databases, you'd be familiar with relational databases. And Bertrand Russell introduced the concept of relations, that you could have siblings is a relationship for which you could have multiple people in that, whereas before the logic of Plato was about properties of individuals. So Socrates is a man, men breathe air, therefore Socrates breathes air, that kind of thing. So what they were trying to do, their objective was to give a rigorous foundations of mathematics. By rigorous, it's what I was saying earlier, completely unambiguous. And they were part of the forefront of making it unambiguous. And they succeeded, and if they didn't do that, we wouldn't have computers, we wouldn't have computation. And they did this by first examining how people thought. And what this 2,000 plus page, and I've actually picked it up and looked at it, was a precursor of software. Now that's not what either of these guys would have told you they were doing at the time. They were just doing logic and trying to refine foundations. And as all logicians, their emphasis is on truth. But computing, the emphasis is on calculation. And in particular, with computers, we're trying to do work. We're trying to build machines that do work. And a property that they must have is that what they're doing is true, or else they have bugs. Of course, and all software has bugs. Like, why can I not get this to be full screen? For example. All right. Now, the mathematical basis for computing is actually pretty simple. For those of you who are not deep into computing, it doesn't take a whole lot. You start with a set of symbols. So the integers are the standard set of symbols, the positive integers. That's all you really need. And you need memory. So you need some place where you can read and write symbols, these integers, and they persist in time, and you can go do some work and come back to them and read them, and they're still there. So a very basic requirement. It's like taking a pen and paper and writing it on a piece of paper, except you can, actually pencil and paper would be better because you have the ability to erase and write something else. So you have this memory idea, and that wasn't really part of mathematics. So that was a fundamental step in introducing, going beyond traditional mathematics. Traditional mathematics barely had the concept of process. It was really just more relations of numbers. And so in addition to the memory got specialized into two different categories, data and instructions. Instructions is another key addition that computer science brought. It's the idea that you take action and do things. That wasn't really in mathematics. And you do some computation and you create a new symbol from other symbols. And so the standard example is arithmetic. You take two numbers, you add them together, you get another number. And if you can do addition and subtraction, that's all you need. And then the additional component is you need the capacity to decide what instruction to execute next. And that's all you need for computing. So you've got at least three things, which I've got in capital letters, that you didn't have in traditional computing, and now you can compute everything that's computable, or everything that we think we mean by computing. So just like the logic is simple, I didn't spend too much time on it, the basis for computing is simple. And you apply that widely, and you get the miraculous things that we have today, which I'm going to be touching upon. So just to finish this, the Turing machine. So Alan Turing, you may have become some awareness of because of the Enigma, the movie that he's in. I can't remember the name of the movie right offhand, but the Enigma machine that he worked on during World War II. So it was also the case in computer science. He was known far more for his theoretical model of computing, which people called the Turing machine. And then another mathematician, he was at Princeton, von Neumann, created an alternative solution, and that's the one that we've used, all our computers are built on. But they essentially came to a conclusion, and there was others. There was maybe, I think there was 8 different ways of doing computing, and then they realized they could transform any one of the ways into the other ways. So there was only sort of one notion of computing. That's what it turned out. Let the clock go forward a whole lot, and you get our digital technology revolution, and I'm showing you images of the upper left, a computer chip, actually a printed circuit board that has lots of electronic components. To its right, the Apple iMac, and next to it, the iPod and the iPhone. And then in the lower left, you have a machine room that has racks and racks and racks of computers, hundreds, at least thousands. And then the picture in the lower right is just trying to artistically convey the idea that the entire globe is wired up, that can communicate. And all of that happened just because of that little bit of foundations of people wanting to have precision and lack of ambiguity and pursuing basic knowledge. And out of that pursuit came something that was completely transformative to society. So one place that it's transformed, I mean, I'm not going to, I could spend a lot of time going through every example of where it's transformed, but let me just point out a couple. So on the left is a MRI, so that's a big, huge magnetic machine, and if you put in the right components for it, you can use it to measure brain activity. And in the lower left corner, those colored pictures are cross-sections of a person's brain, and the colored regions, or the degree of color, indicates how much activity there is in that. So this has given us a way to peer into our brain and see what was going on and start making hypotheses. And this was invented around 1990, and it's being used mostly for research, but my project at Baylor College of Medicine is trying to use this to develop yet another treatment for PTSD. Now, in the upper right, you can't really tell what that is, but that's a robotic surgical. So surgeons can use this to do surgery where they're not doing direct hands-on, but they're using a remote control for that. And then in the lower right is someone who obviously had lost his arms, and those arms have now been replaced by robotic arms. So some pretty significant advancements. And in the case of the prosthetics, you can start asking a question which I'll bring up periodically, which is the blurring of the boundary between humans and machines. And that's a trend that's going on now. Not dramatically, but it continues to pick up momentum. And right now it's driven usually by people who have lost their limbs, or some of them. Okay, another use of computers you probably are not aware of, but it's had huge impact. And you're not aware of it because you're not in the right profession. And the profession that I'm referring to is usually called computer-aided design. Everything that's manufactured today is first designed and tested on a computer. So these pictures I have here are for aircraft. They're one of the more interesting cases. And in the upper left, you can just see some geometry for an aircraft. It's a little hard to make out because this is a line drawing where you're not filling in the interior of the surface. You're just trying to show what the underlying mathematical or computational mathematical structure is. So it turns out that it's enough, just in the case, like as with logic, there's actually only 16 Boolean functions you have to worry about, or 10 if you ignore some duplicates. And there's only 3 categories of instructions for computing. For doing physics simulation, you start off with usually polygons, and which are defined by points in space, 3-dimensional points. So a triangle, if the end of my fingers are points, then those 3 points here can define a triangle, and now you just make a lot of those triangles. And so in computer games, it's really quite common to have millions of triangles representing the characters and the buildings and all of that. And that's all you need for most of the things where you're doing computation on geometry. Now, the colorings that you're seeing here, so in the upper right, that's a jet engine, and those colors indicate the degree of temperature. And so usually the color scheme they use, this is called false color because there's nothing, you're not seeing this when you look at the real object. That's why you need computers. So usually the red is hot and then the blue is the coldest. So this was temperature simulation. So any of your jet engines are designed with computers and they're tested with this simulation. And it's all just using physics to see what would happen. And it works well enough that we're flying in all our airplanes, and almost all the time they stay in the air. The lower right picture, those long streams, that's the airflow. Obviously with airplanes, how they interact with the air is critical to how they work, their ability to have to elevation. And the picture on the right is a more detailed analysis of one of the blades in the engine, jet engine above it. Not specifically that jet engine, but in general, jet engines. Okay, a completely different category from a use perspective, but not different in terms of the technology. It's essentially the same technology at its base as what's used in the airplane design. Well, you don't have to do design with weather, but in terms of the simulation. So you occasionally see some interesting simulation pictures on TV, and the pictures on the left, the upper left, that's actually computer generated picture of one of the hurricanes that caused us a lot of trouble. I can't remember which one right offhand. But you can do really detailed computations, and below the hurricane is the computer simulation of the eye of the hurricane, or a hurricane, maybe not this particular hurricane. So if you can see it clearly enough, you can see that there's really quite a bit of detail. And then over in the right is an instance of a tornado that's being simulated. So the theme here is you can use computers to simulate the physical world, and you can learn a lot about them. And that's going on as we're speaking. And it's very important. Now, I could just keep going on and on and on, because just from a personal perspective of observation, I can't think of any area that hasn't had some computer simulation applied to it. It's not like I've really tried to answer, is there some area that is not getting simulated, but it seems like everything is getting simulated. And I had many ways of seeing that, but one was when I was at UT, one of the things I did was I was in charge of the visualization lab there. And so we had many people using our huge arrays of computers to generate pictures like these. Not necessarily weather, but analogous in certain other areas. And so it was pretty much anybody on campus who had any problem that had either a scientific 3D basis or any engineering. So this, I don't know if you can read this slide too well, but there's at the top, because I don't even have my cursor, I don't know what happened. There's physical sciences, it's astronomy, geoscience, and there's social sciences, sociology and psychology. Not sure how that's getting simulated in this particular case. Life sciences, biology, physical sciences, like I was just showing you, physics and chemistry, and then just some pure mathematics. And you can modeling is done down at the particle level, so there's been simulation of the nucleus of an atom, so simulating in terms of quarks, if you're familiar with those at all. So that's below neutrons. So neutrons and protons are made out of 3 quarks. So you're talking about going inside the atom and doing simulation. So you can't get any smaller, given our current theories. So that's the lowest level. And then there were a lot of people at UT, not a lot of people, there were some people at UT who were simulating galaxies and simulating galaxies colliding and what the gravity field of each galaxy would do in terms of shaping the motion. So I think galaxies is a good stand-in for the largest scale, quarks for the smallest, and kind of everything in between. So this has been going on now for decades, but it's not something that is terribly visible to the public. What is much more visible is entertainment. So you've got video games and you've got animated cartoons, but not just animated cartoons. Any of the special effects today, so if you see like the Marvel movies, they never look like cartoons, even though Marvel came out of doing a cartoon culture. They look realistic. In fact, they're so realistic that nobody can tell what is computer generated and what is not, except for the people who are sitting there generating the imagery. They know what the difference is. So that's another area. Now getting a little closer over to AI, but not quite there, is virtual and augmented reality. So virtual reality is where you use computers to synthesize your entire sensory input. So vision and sound and touch. Touch is a little tricky. Vision and sound is doable, very doable, has been for a long time. And so we're using the same kind of machinery, so the same machinery we're using to simulate the airplane, that kind of stuff, lots of triangles, is used in doing virtual and augmented reality. And in terms of this picture, so in the upper right, that's a virtual reality headset that you wear where you have a display for each eye and it's shining a computer-generated imagery into each one of your eyes, and as you move your head around, it tracks the motion of your head. And then below this is an example of augmented reality, or they're trying to demonstrate. So once again, you have an aircraft. I don't know if you can see it terribly well, and people with headsets. But the difference is that the individuals are able to see the physical world with the virtual laid on top of it. And so that gives a different experience. Now let me see if I can switch over to a video of software, of a demo that I created using software that I wrote. Okay, so this is kind of ignore, so you've got a bunch of things going on here. Ignore the green lines and the white lines for a moment. And what you're left with is a model of the San Francisco Museum of Fine Arts. And this is a cardboard model so that I could use it in my house. I couldn't fit the entire museum inside my house very easily. So we get a small little cardboard model. And we created a CAD model of this cardboard model. And if we had had an affiliation with the museum, we could have gotten the CAD model from the architecture firm that was contracted to build this originally, which was Bechtel. You may have heard of Bechtel. And they built this. And so all the buildings they always do CAD models first. And they build from the CAD models. Now the additional element here is that usually historically, the people who did the CAD models are sitting in an office someplace, and they're never on the construction site. And one area of using augmented reality is to try and bring the CAD model out into the construction areas so they're not just essentially doing blueprints, but they're being projected onto the 3D world. And that's what's happening here. So now these green lines and the white lines are all projections of the CAD model out in the world. And the red ones, there's a really good, the green ones indicate a good match between the original CAD model and what's been constructed. Because a big issue in construction is discovering mistakes. So there's estimates that about a third of the money spent, a little bit less, but in the order of, say, 30% of the money spent on a particular construction project goes to fixing errors that they just introduced. And so the idea here was to project what the model would be while they're doing the construction and have them catch their errors really soon before they've done a bunch of construction on top of that. And one little other detail about this particular picture, if you can see it, if you look in the upper right corner carefully, you'll see that there's a part of the building that's transparent. You can see down and see the ceiling. The reason for that is that that part of the building doesn't yet exist. So that's the to be built building. And so there's two reasons I'm showing this. One, I wrote it, and you can see what I'm doing. But the point, it illustrates the point I'm wanting to make, and that is, there's a bigger point, and that is that the world out there can be represented by mathematics and computation. And it's always there, and there's no reason why most of you would see the world that way, but I see the world that way. I walk around and I see the geometric representation of it. I can essentially see what I'm showing you here, in effect. Not exactly, but within the neighborhood. So it's really more a matter of conditioning. It's really there, but it's invisible to you. So there's a really fundamental fact that things in the world can be represented with combination of mathematics and computation isn't instantaneously visible to the naked eye. You need to have it brought out. But it's a truth, and it's a very important truth. And I have gone, in my career, I have lived through, starting from a posture where we had no idea or very little idea to the extent of what I'm saying is true. The extent of what I'm saying is that we've ended up being able to model practically anything we want to model with computers. When we started out, we had no idea what we could model. Or we had some idea, but not to the extent that we've been able to actually achieve. So before I leave this picture, this image, just show you the dynamic. So it's going to start rotating in a minute. And the building is sitting on a turntable. And now it's rotating, and you're like, okay, fine. But what's happening there is we're tracking the rotation. The reason why those green edges look like they're affixed to the building is because we're correctly computing every frame the position of the physical camera relative to the rotating object. So it doesn't seem like we're doing anything additional because we're taking advantage of what your expectations are. Only when every once in a while it gets off, and that's because of noise in the camera. But we're every frame determining the location of the physical camera in relation to this model that's rotating. And that's what's critical to do the augmented reality when you're moving around and you're wanting to have a mix between the physical world and the virtual world. So this is an explicit demonstration of a mix between those two. In fact, another term for this rather than augmented reality is mixed reality. All right, so some people who are doing augmented reality, their goal is not to have you wear bulky glasses, but to do something, either have glasses that look stylishly nice, like the ones in the top row, or to go even further and have the graphics projected onto a contact lens. So you put the contact lens in your eye, and now you don't need a display. There's no display like this guy here. You just have these contact lenses, and all the computer graphics is generated on the contact lens. All right, now let me slide more explicitly into AI. And AI is the part of this whole problem where we're trying to capture what the human brain does naturally. So this began with the metaphor of brain as computer. And you have inputs, you have our 5 senses, and you have those are the external inputs, and then we have internal inputs like the position of all your muscles, your joints, how much energy you feel like you have, temperature, all this other things. That goes into information processing, that's the brain, and memory formation. And then output is muscle control, like me walking, standing around, doing random motion. That's control from my brain. So we have the input part, processing part, output, and that's what all the computer programs do. So that general structure is just the general nature of computing systems. In the case of the human, genetics determines the architecture, in general, and experience programs the neural networks. Now that's a very broad, rough approximation of what's going on, but it's good enough to get some feel, I hope, that there is a strong parallel between biology and what computer science and computer engineering devised in terms of exploring the space of computation. Now, one other element of the picture that is lurking off to the side that I just wanted to mention is gene editing. I just have one slide on gene editing. That's unlike software. I mean, it has a lot in common with software. It depends on where you want to draw the line. But gene editing, I'm sure you're aware that so what's on the left here is a picture of the double helix for DNA, and it has these outside ribbons that are made of sugar molecules, and then it has what looks like stairs that connect the two outside ribbons. So it's like the outside are handrails for stairs, and each one of the stairs is a piece of DNA, and there's 4 types of molecules that make up the DNA, the double helix. And this doesn't matter what the names are, but they have 4 different colors. And that's the code for us. That's coding for us. So there's 4 possibilities at every location. And so that's mathematics. You can represent that with the idea of bases. So our normal numbering system we use is base 10 because we have 10 fingers. And so we talk about 10 and 100 and 1,000. So we're multiples of 10. And you can do that for any integer. You can do that for 4, and that's a base 4. Computers are built on base 2. And they're built on base 2 because that's the simplest, and it's enough. You just need more than 1. And so going down to the very lowest level of our biology, which is the DNA, you have elements that are the same as in computer science. CRISPR is a way to edit that structure, so it shares, the element that it shares with software is the fact that you can change it. What it doesn't share with software is how easy it is to change. It's a much more elaborate process, but of course that gets easier all the time because there's researchers pushing on how to do gene editing. Okay, now returning explicitly to AI. So robotics is there's a lot more to AI than just robotics, but I think for this talk it's easier just to focus on robotics for a second because people can relate to it. Robots are explicitly a piece of technology intended to mimic humans. And it begins with mimicking the skeletal structure and muscles. Of course, robots are not implemented with flesh and bones. They're implemented with other material than that, that's inorganic, that's not growing. But it's been designed based upon our skeleton. So we have bones and we have joints and et cetera. And then the robot has motors for determining the orientation of each one of those joints. So that's like the first stage, just to get something that's sitting there. Just repeat kind of what nature has done to a certain extent. And people have been working this, every aspect of AI have been working on it since the 50s and making gradual progress. And I remember a guy that I actually hired to help on a project we had at Bell Labs, who was a leader in robotics, and in fact, I've seen the military using some of his robots that mimicked essentially dogs for, quadrupeds, and could climb up rocky terrain. And it took his crew, decades to get that to work. So all this stuff takes a long time. So even something as basic as the skeleton muscle simulation. But in addition to it, you need computer vision. And I should say that the demo I was showing you just a minute ago on the museum, that was using computer vision. And computer vision has always been at the first level of AI. And what the first step on computer vision is to find simple elements in the image like edges. And let me just go back briefly. To my video. So those the green and white and the yellow, not yellow, green and white, and actually there's some red edges in there. That's a result of computer vision. It takes an image, searches through the image, and finds edges. And then those edges are used to, in the process of determining the relationship of the physical camera to the physical model. And all AI that's dealing with the world out, the real world, usually has to start with computer vision. Okay, and there's a lot to computer vision. Then there's the robot needs to move around, and that requires planning for motion, and which is a whole area in robotics of itself. Then you have object recognition. What objects are you encountering? And then similarly, but a completely different mode, you have speech recognition. And in the case of speech, since humans can generate speech, and we're trying to replicate humans to a certain extent, then you can use speech synthesis for sound. You can't use, there's not the object synthesis, so there's not a corresponding synthesis stage for 3D objects unless you could use 3D printing, but it'd be pretty slow. Okay, now AI has approached their problem from one of two directions, either top-down or bottom-up. So top-down was the dominant method for a long time. Now what do I mean by top-down? Top-down was kind of what the philosophers did originally. So when the philosophers came up with their logic, which became formalized, they just observed themselves. Philosophy was always based on introspection. It was never a rigorously scientific process. And AI researchers for decades would try and, through introspection or maybe more formal methods from psychology, try and ascertain how the human was solving problems, but doing it at a high level, meaning the level that a person might be able to describe their experience. So with their introspection, they say, well, I'm looking over here and I'm seeing some edges, and then I'm assessing as I move around, my brain is good at taking the sequence of views and the edges and how they change in time, and from that I can get a 3D world. It was sort of the speculation. Now that's not, that's how the body operates, it functions, but it's not how it got there. It got there through a long process of evolution over millions and millions of years. And that did not have intelligent design, didn't have any design explicit, and happened as a continual process. And that's what I'm referring to as the bottom up. And this starts at the lowest level, which is the neuronal level. So here's an artist's picture of a neuron. So these are the building blocks for the brain. You have a cell, you have a bunch of inputs, that's what these long guys are toward the center, and then this really large one is the single output. So you have input, you have some computation in the cell body, which is basically addition of all the inputs. It adds up all the inputs, and it gives a weighting to each input, and that weighting comes from learning. And then through some magic that we only are beginning to understand, this process of taking a gazillion neurons, connecting them up, is what is required to produce what we are familiar with as our consciousness. What the neurons do and what we've been able to mimic in AI, we call it machine learning. And it turned out that rather than do the top-down where a human comes up with the answer and deduces it and it gets implemented, they used a bottom-up. And the bottom-up was really repetitive learning. So how do you, if you learn to play a musical instrument, you started as a kid, if you want to get really good, it takes years. And you practice, maybe not every day, but you practice frequently, over and over and over. And if you think about how you've learned stuff, and you know this already, it's by repetitive practicing. And that is how the human brain learns new things. So AI decided, well, maybe that would work well, for doing the artificial version of this, and indeed it has. And so the whole machine learning, it is doing learning like we do, and it uses the trial and error. So try something, measure how much error is there, and then adjust the weighting between the different inputs in order to improve your performance. So just to give you a little quick idea here, so we wanted to classify this very simple artificial problem. We wanted to classify people into short and stout versus tall and thin. So if you have one dimension, which is their weight, and another dimension, which is their height, and you plot the points, you discover they kind of cluster, and here the blue guys are tall and thin, and the others, these guys are short and stout, I believe. And you can do this, and you can find a line that separates these two groups, and when you then have a new person come in, you put their parameters into this table, and you see which side of this line it's on, and from that, you can then determine whether they're short and stout or tall and thin. And that's kind of how you can do a lot of machine learning that's happening. It's I guess gave you a very brief example of that. Okay, to get a little more futuristic, so we've reached the stage of superhuman AI. So what this means is that AI can, in certain special cases where they've done a lot of this learning, and the learning requires pumping in lots of data, and been able to, in certain areas, outperform humans, experts. And the example of this, I think it got the most press, was in the case of Jeopardy, that the Jeopardy winners got beat by the IBM machine. And now that's been extended to other games like Go. Chess was done a long time ago. And then another area that doesn't have anything to do with games is taking MRIs and determining whether there's any indication of cancer. And now the machine learning has gotten to a point where it can do better than the experts. But it got there. They didn't just like turn on the power and say, solve this. You had to have experts saying, this is an example of having cancer. So you had to have people in the loop deciding whether it was cancerous or not. You do this with a lot of input, and the neural nets learn this, and then once they've been trained, then they can go off on their own. You can give them new examples, and they can identify it. So it's kind of a weak form of intelligence. It's not something they learned on their own. It's trial and error. It's a human saying, this one is cancerous, this one is not. So you still have that in the loop. But that's where we are, and it's made a big difference even with that much, because once you've got that capacity to recognize things over in the computer, then you can replicate it across a bunch of computers, and you can have really high performance. And that kind of stuff is how Google picks the ads in their web pages for you to show, because they're like, oh, well, he's interested in, or he or she is interested in this particular area of like cars. I just bought a new car, and now it's always showing me ads. I'm sure you've had the same experience, always showing me ads of cars, and it's just taking in the input and learning in this very, very simple way. Another car example. Are we doing on time?
We just have about 3 minutes left.
Okay. So self-driving cars have received a lot of attention. That actually uses technology similar to what I was showing you with the museum tracking. I won't really go into it, obviously, but there's a lot of overlap between the technology I'm using and what you need for self-driving cars. There was a huge amount of attention paid to that, and now it's kind of off to the side. It's still happening, and I'm not sure exactly why there's the diminished attention, but there were a few accidents, and that everyone's kind of recoils. They're like, wait a minute, we have 30,000 accidents every year. Why are you getting freaked out about this one or two or three that are a result of the AI making a mistake because they're really working well? Well, that's just how humans are. That's how we react to that. All right, now to get more speculative, off into the future, AI threats. So there's the elimination of jobs by automation. So self-driving cars are a good example. Long-range truckers are concerned about their jobs being taken away at some point. Hasn't happened yet, but that was sort of one of the ones that people pointed out. So that's not a very good one, a result. We're not really, I mean, we've always had the problem of automation putting people out of work, and we've never really come to grips with it. And part of our current political situation is because we never came to grips with that fact. We just said, okay, the free enterprise system represents all goodness, just let it run, it'll produce goodness. Well, not the case. Okay. Other examples of huge impact were fake news. And then there's another one that doesn't get a lot of attention, and that is you get a biased data. So the great example of that was Google really wanted to see if you didn't actually have a human tell the machine anything about what they were looking at, what it would do. Well, it turned out it was learned how to do one thing, and that was recognize cats, because people put tons of cats pictures up on the internet. So that's an example, a gross example of statistical bias. Okay, longer term, we all worry about killer robots. Well, we don't spend much time worrying about killer robots, and it depends how much sci-fi you watch. But it is a concern, and it's a concern of people who are very serious about this topic, and there's a UN-sponsored effort to determine how to have safe AI. We don't want to have the AIs take over and decide, well, you know, you evolved and you're really kind of cute, you know, you human beings, but you're so flawed because of this process that created you that we'll just eliminate you because we don't need you anymore. And Schwarzenegger was sort of a pioneer of that, in fact, with the Terminator series. All right, let me just finish with a big question. Can we ever have machines that are conscious? I think I'm highly biased.
What machines that are what? Oh, conscious.
Conscious. Yeah. So we're conscious entities. We're generating a stream of consciousness as we live, and we can introspect. So the thing is, can we build machines that are conscious? Well, the answer is we have no idea. But it's going to take, but there are people working on this who are very, very serious and skilled people. One of them is head of the Allen Brain Research Center in Seattle. Allen being Paul Allen, the co-founder of Microsoft. So they have tons of money. And I believe there's an issue at the very fundamental level of reality that has to be resolved to this, and that is what the relationship of, what are the fundamental ontological categories and how do they relate to each other? So the standard, I'm sure you haven't spent much time thinking about this, and if you didn't take philosophy, you wouldn't have spent any time, but the standard categories are matter and mind. So we're like, oh, here's matter out here, and then there's this thing up here, mind. What's the relationship between those two? What I believe, what I'm advocating or trying to establish more evidence for, and there's plenty of people on my side on this topic, is that you need to include mathematics and computing as sort of the first order category of reality. That I was showing you all these applications where we can use computers to simulate, but I was ignoring the question, how is that possible? And the position that people like me have, which is sort of realistic mathematical realism, is that it has to be a fundamental property of reality that it's representable by computing and computation. And until we answer that question, do not believe we'll be able to answer the question of whether we can have conscious machines. And I will just leave it at that, because I bet I'm out of time.
And indeed we are. Dr. Naylor, thank you for your presentation. Thank you for your work in this very important area. And may we all transition to this new world in a safe and ethical manner. Thank you very much.